Hello dear learners, I'm Zinnah, a chemistry teacher. Today I'm with mass of tiny particles. Here get a notebook. This is 2 kg, and if you measure mass of a smaller object, here this mug, this is certainly a few grams, not kg. And think about mass of very tiny particles, suppose here atoms or molecules. In the conventional scale, kg, gram, if you go for measuring their masses, you will get 0 because they're so tiny. Though they are tiny objects, but they are particles, they're matter. So certainly they have masses. But how to get their masses? And today's topic is how to measure or estimate masses of very tiny particles. Sense of mass. When you get an object in your hand, you may be feeling little pressure, and this gives the sense of mass. And when you get anything with mass, then we may be thinking of measuring its mass or think of the amount of mass. We use devices to measure masses of things. And how do you measure? We use different units mass to compare masses of objects with. We use ton, kg, pound, gram, milligram, or for the small one is microgram. Mass of different size with relevant unit masses. If this is a chair, then we better measure its mass in kg. If this is a small pen, then we think of measuring its mass not in kg. Better is gram. If this is a big one, then ton could be more suitable. For the very small one, suppose this is a fly, then milligram is better. Can you think out of the box? How do you think the mass of a star? Or how do you think the mass of an atom? Puzzled here. Unconventional masses. The mass of a star. What should the mass of a star be compared with? And what should the mass of an atom be compared with? Do you feel comfortable to think the masses in conventional mass units? Certainly not. Relevance matters. We use 1 kg when this is relevant to the mass of an object. This is 1 kg here. We measure mass of a chair in kg. We measure mass of a dumbbell in kg. We measure mass of a table in kg and mass of a person in kg because these are all relevant. Mass of a tiny particles, the mass of a tiny atom is relevant to. If you think of measuring mass of a tiny atom with ton, this is not relevant. If you think of mass of an atom with kg, this is not relevant. Is this relevant to milligram or microgram? No. This is better relevant to another atom because mass of a tiny atom is small and mass of another tiny atom is also small. So they are relevant. Carbon has 3 isotopes: carbon 12, carbon 13, and carbon 14. Carbon 12 is most abundant and they have chosen carbon 12. But the mass of a carbon 12 is 12. If you divide this with 12, you get 1. So the mass of a carbon 12 divide 12, you get 1. This is carbon scale. This is used to measure mass of all tiny particles. Mass of tiny particles relative to carbon scale are called relative masses. This is the unit mass, carbon scale. Mass of an atom of oxygen is 16, means this is 16 times heavier than carbon scale. A molecule of oxygen is 32. This is 32 times heavier than carbon scale. The mass of water molecules is 18 times heavier than carbon scale. Sodium ion here 23 times heavier than carbon scale. Chlorine 37 times heavier, and chlorine 35 times heavier than carbon scale. Out of this, you get these 3 atoms. 3 are similar because these 3 are atoms, and their masses are called relative atomic mass. And 2 others are also similar. These 2 are molecules. We call their masses relative molecular masses. And now look at these two two are both chlorine atoms, one with mass 35, another with mass 37, because these two are isotopes. But if someone asks you what is the mass of chlorine atom, then what will you say? This time you need to average them, and we're going to average them. So relative atomic mass is basically the average mass of the atoms of an element divided by carbonate scale. If you apply this for chlorine, you get average mass of chlorine 35 and chlorine 37 divide carbonate scale. And let's try to average 35 plus 37 divide 2, and carbonate scale is 1. You get 36, but this is not right, because you cannot think of just two chlorine atoms in nature. In nature, there are many uncountable chlorine atoms, and when you need to average them, you should consider all the atoms of chlorine in nature. With the natural composition of the isotopes, we can easily calculate their average atomic mass. Here you get chlorine 75% is chlorine 35, and remaining 25% is chlorine 37. Think of a balloon with 100 chlorine atoms. Out of 100 chlorine atoms, it certainly have 75 atoms chlorine 35 and 25 atoms of chlorine 37, and one with mass 35. So 75 atoms mass together is 75 into 35. You get 2625, and mass of 25 atoms would be 25 into 37. You get 925. If you add them together, you get 3550. Divide them with 100 because you have 100 atoms, so you get this average. But simply you can calculate as 75 into 35 plus 25 into 37. Divide with 100, you get average. This is how simply you can make average. Get some exercise. First one, lithium consists of 7.5% of lithium 6 and 92.5% of lithium 7. Calculate RMM of lithium accurate to 1 decimal place. Get another example. A sample of hydrogen consists of 99.98% hydrogen 1 and 0.0156% of hydrogen 2, and remaining is hydrogen 3. Calculate RMM of hydrogen in 4 decimal point. This is how we get the masses of tiny atoms. We call them relative atomic mass. But how to think of the mass of the molecules? Most of the molecules are very small, and they are little bigger than the atoms, but they are still small. So their masses are also considered in carbonate scale. Relative molecular mass. We already got relative atomic mass as average mass of the atoms of an element divide carbonate scale. But if you think of relative molecular mass, then atoms should be replaced with molecules. So we get average mass of the molecules of an element or compound, because molecules can also be compound, by carbonate scale. Apply this for oxygen. Average mass of the molecules of oxygen divide carbonate scale. Apply this for water. Average mass of the molecules of water divide carbonate scale. Calculating relative molecular masses. You got relative molecular mass as average mass of the molecules of a substance divide carbonate scale. But simply you can calculate relative molecular mass by adding relative atomic mass of the atoms in the substance. For example, relative molecular mass of hydrogen chloride is hydrogen here 1 plus 35.5. For chlorine you get 36.5. Similarly, for sulfuric acid you get 98. For aluminum carbonate you get 234. But one thing here, relative molecular mass should be replaced by relative formula mass, because the ionic compounds are not molecules. So when they are not molecules, then it's not better to call them molecular mass. So when you use relative formula mass, that better fit for the molecules and the substance without molecules. These were all about the masses of very tiny particles. I think this video has made your concept of the masses of very tiny particles clear. And thank you for watching this video, and thank you for being with us.